Polynomial optimization problems today. We did a little bit of it on Wednesday. And just to remind you of what's coming up, on Monday, I'm going to give you quiz 1 as a take-home, and it will cover lessons 1 through 7, so everything that we have done up through today. So I'll give that to you Monday. It'll be due the following class Wednesday. It's pretty short, yeah. And then your trucks project is due the following Monday, September 28th. Okay. And your project check-in day is this coming Monday. Okay. So you'll have a project check-in day to sort of check in with your classmates, check in with me, get as much done as you can. And then from that point, you have a week until it's due. All right. So we were at class 7, it's where we left off. We did the beginning. We were talking about relative and absolute maximums and minimums. So relative maximums and minimums are any peak and valley in a graph is a relative maximum or minimum, or relative extrema. And then the highest point on a closed interval is called the global maximum or the absolute maximum. And the lowest point on a closed interval is the global minimum or absolute minimum. All right, so we looked at the graph of a polynomial. Well, we looked at the formula for a polynomial, and without looking at its graph, we figured out where its global maximum and minimum values are. So we did that by finding where its local extremes are, and local extremes always happen at places where the derivative is 0. Why is that? Why is the derivative being 0 connected to the location of a local maximum or minimum? Yeah, there's a peak on the graph, which means that the tangent line has a slope of 0. Horizontal tangent line has a slope of 0. Okay. Or if the derivative is undefined, that can also be a local maximum or minimum because you might have a sharp corner, right? Good. So we set the we took the derivative of f, we set it equal to 0, and we found x values where the derivative is 0. That means we found x values where our function has horizontal tangent lines. So these x values must be are possible locations for maximums and minimums. And so then we looked at the y values at those x values, f of 2 and f of 3. And we also looked at the y values at the end points of the interval, because those are also candidates for a global maximum or minimum. We took the highest one, the global max, and the smallest one to be the global min. All right, so now we're going to look at this word problem. Here's our first of many optimization problems. So this is going to be a theme throughout this whole course, is solving optimization problems. And your trucks project is also an optimization problem. Once you get to number 14 of the trucks project, they're asking you to find the optimum speed that the driver should drive the truck at in order to minimize cost, right? So here's a math book printing optimization problem. A math book is to contain 36 square inches of printed matter per page. The margins are supposed to be 1 inch on the sides, 1.5 inches on the top and the bottom. Find the dimensions of the page that will require the minimum amount of paper, and find what that minimum amount of paper is. Okay. We'll use our first sign chart at the end. We're going to let L and W be the length and the width of the part of the page that is printed on. All right, so good place to start with these things when it's geometric is to draw a picture of it. So this is the printed part of my page, printing on the whole thing. All right, so we're letting L and W be the length and the width of the printed area. And then we also have margins, right? So we've got 1.5 inches along the top and the bottom, and then 1 inch along the sides. So then, what is that length? Yeah, L plus 3, because this is 1.5 inches and this is 1.5 inches. So you take, this is L, add 1.5 and 1.5, and you get L plus 3 for the length with the margins. And then what is that distance? W plus 2. Good. All right, so we've got a good picture of what they're describing here. And we are supposed to find the dimensions of the page. So I'm looking for the dimensions of the outer page, the whole page, W plus 2 and L plus 3, that will require the minimum amount of paper. How do you measure the amount of paper that's being used in inches squared? Yeah, we look at the area of the page. That's how you determine how much paper is there. And the area of this thing, the area of the page would be what? Yes, it is 36 square inches, yeah, but how do you calculate area in general?
L plus 3 times W plus 2.
Yeah, the area of the page in the book is going to be L plus 3 times W plus 2.
Is the 36 inches of printed matter supposed to be
yes.
Inside the box? Or
yes.
The whole page?
Inside the box. Yeah, inside the box
Okay.
is the 36 square inches. So what I'm trying to do is minimize the area of the whole page, right? So this formula that I wrote for area, I want to make area as small as possible. So this is what I want to minimize. So I'm looking for a minimum value, right? We did that with the polynomial problem. We can find maximum values and minimum values. We already did it. We had a formula and we have a procedure for finding maximum and minimum values. But what makes this one a little different or harder is that there are two variables, right? This isn't A as a function of X. I have L and W. So this is the function I want to minimize, and I have what we call a constraint. And that's that the printed area has to be 36 square inches. How would I calculate the printed area? L times W, length times width equals, has to equal 36. So if I took this equation and solved for one of my variables, doesn't matter which one. Let's say we solve for W, it would be 36 over L. That would allow us to go back up to our function that we're trying to minimize, replace the W with a 36 over L. Okay, so area is L plus 3 times 36 over L plus 2. So I just did a substitution based on our constraint. With me so far? Okay. So this is the thing I want to minimize. I would like to minimize this. So in general, finding maximums and minimums, you have to find the potential places where those might occur. Potential places where you might have a maximum or minimum are places where the tangent line is horizontal, right? Because that could be a maximum or a minimum, or where the derivative is undefined. Okay, so horizontal tangent lines happen when the derivative is 0, so I have to take the derivative of this, set it equal to 0, find potential locations of maximums and mins. Those are called critical numbers. So first thing I'm going to do is FOIL this out, because we only know one rule for taking a derivative, and it's the power rule, right, so far. So I'm going to multiply that out so that I have a polynomial to start with. So L times 36 over L is 36 plus 2L plus 3 times 36 is 108. And it's over L, but I'm going to write it as L to the -1 so that I can apply the power rule. Same thing, right? and then plus 6. And I'll simplify this one more time. I can combine 36 and 6 to make 42 plus 2L plus 108L to the negative 1. So this is a formula that tells me the area of my page based only on length, based only on the length that we choose. So if I want to minimize area, I have to find potential places where minimums can occur. That's where the tangent lines are horizontal, because those will be the peaks and valleys of your graph. So horizontal tangent lines happen when the derivative is 0. So what's the derivative of 42? 0. Derivative of any constant is 0. So what's the derivative of 2 times L? 2. And then for 108L to the negative 1, bring the negative 1 down, multiply by the 108. So I have negative 108. Copy the L, reduce the exponent by 1, and you get negative 2. So that's my derivative, and I want to set it equal to 0. It's called the power rule. Yes. So from A to A prime, did you watch the videos from the past couple classes? Because I know you weren't here. Yeah, I'll go over it with you in a few minutes. It's kind of involved where the power rule. Yeah, I'll do it with you separately. Okay, so I would like to solve this equation where A prime equals 0. So I want all my L's to be on one side, numbers to be on the other. So I'm going to add this 108 L to the negative 2 term to both sides. So I get 2 equals 108. And I'm also going to rewrite it as 1 over L squared. Instead of times L to the negative 2, divide by L to the positive 2. And I'm running out of room. You probably are too. I'm sorry. Okay, so to finish solving this, multiply both sides by L squared. So I get 2L squared equals 108, which means L squared equals 54, which means that L is approximately plus or minus whatever the square root of 54 is. 7 something. 7.35. All right, which of these can we just get rid of? The negative, because this is representing the length of a piece of paper. Can't be negative, right? So just ignore the negative. Just 7.35. Okay. So we have a potential maximum or minimum at 7.35. We don't know which. We just know that there's a horizontal tangent line there. Could be a maximum, could be a minimum. It actually could be neither. This is just a potential place that there might be a maximum or a minimum, because we know there's a horizontal tangent line here. We call this a critical number. To figure out what it is, to determine whether it's a maximum, a local max, a local min, or neither, we make something called a sign chart. So I'm going to make a sign chart, and I put on all of my critical numbers. I only have one in this case, 7.35. And I'm going to chart the area. Like I'm going to find what the area is at various places in relation to a length of 7.35. So remember, if you go back to our area formula, the area of the page is L plus 3 times W plus 2. So I'm going to analyze each of these, or actually maybe I'll use this one, L plus 3 and 36 over L plus 2. So the area is made up of two factors, L plus 3 and 36 over L plus 2. So I put a little fence here. Oh, that's area. Yeah, yeah. Sorry, I don't want to do that. I lied to you. I want to analyze A prime here. I want to look at A prime, which is 2 minus 108 over L squared. Okay, so let's look at A prime.
Are there a lot more steps that are going to happen after this one? Because I'm running.
No. Okay. All right, if I plug in 7.35 or the square root of 54 in here for L, I'm going to get 0, right? I already know that. That's how I got the 7.35. I set A prime equal to 0. So your derivative at 7.35 is 0. Just remind yourself it's 0 there. What if I'm to the left of 7.35? Pick any number you want that's left of 7.35, something smaller than 7.35, and plug it in here. Right. Yes. Yes. This is the slope of the tangent line is 0 there. Yeah. All right. What's a really easy number to the left of 7.35? 7. 0 is real easy, except what's the problem with 0? The derivative is undefined there. So that's actually another critical value. I should put that in, right? The derivative is undefined there. So critical numbers are places where the derivative is 0 and where it's undefined. So we actually have another critical number. All right, so pick a number between 0 and 7.35. 1, that's an easy one to plug into A prime. 2 minus 108 is negative 106, right? All right, so I don't care what the number is, I just know that it's negative. And that's going to happen no matter what number you pick between here. Every number from 0 to 7.35, you plug it in for L, you're going to get a negative. All right, pick a number bigger than 7.35. 8. How about an easier number? Yeah, 10, right? So if I put in 10 for L, then I'm going to be dividing by 100. So 2 minus 1.08, positive or negative? It's a positive number. 2 minus 1.08 is a positive number. And no matter what number I plug in to the right of 7.35, I'll always get a positive number. Why am I ignoring to the left of 0? Because the paper can't be negative. Yeah, can't have negative length. All right, so let's think about A prime and how does it relate to A? Okay. When the derivative is negative, you don't have to copy this part down. I'm just going to, if the derivative is negative, that means the slopes of the tangent lines are negative. So you've got negative tangent lines. If you have a function following those tangent lines, is that function increasing or decreasing? Decreasing, yeah. So here, if I know that my derivative is negative here, that means the original function A is decreasing. And then if A prime, if the derivative is positive, the function itself must be increasing. All right, and what happens when a function switches from decreasing to increasing? Well, you have a minimum value. Yeah. So that 7.35 is in fact a min, a local min. All right, so let's fill in the words here. Here's the required justification that's typical at the end of a max or a min problem. Since A prime goes from negative to positive, right, at x equals, oh sorry, L was our independent variable, at a length of 7.35, okay, A has a local minimum at x equals 7.35. So when you're solving an optimization problem, you should always finish by writing a sentence like this that justifies your conclusion. Yes, thank you. Force of habit. So we got all of this information from the sign chart. Right? A prime went from negative to positive. That told me that my function A has a local minimum at the x value of 7.35, the L value. All right, so the idea behind our sign chart are formalized in a test called the first derivative test. It says, suppose f is continuous and it has a critical number at some x value, we'll call it x naught. If f prime is negative immediately to the left of x naught and positive immediately to the right of x naught, that means that f went from decreasing to increasing, so f has a relative minimum at x naught. And then flip it. If f prime goes from positive immediately to the left to negative immediately to the right, that means that f, not f prime, but the function f, went from increasing to decreasing. Picture a function going from increasing to decreasing. It would have a local maximum. And it's also possible that f prime could have the same sign on both sides of your critical number. And then the horizontal tangent line that you found is neither a maximum or a minimum. Something that looks like that could be something like this, right? Where you've got a horizontal tangent line, but it's not a maximum nor a minimum. Because the function is increasing here, which means its derivative would be positive. Then its derivative is 0 at the horizontal tangent line. And then it's increasing again, which means the derivative is positive again. Okay, so this would be an instance where your critical number was neither a max or a min. And the sign chart for this thing would look like this. This is f prime. You'd have your critical number x naught, and you'd have positive on both sides. Okay, you try some. One last thing. I never officially answered the question, right, about the printed paper in the math book. Right, so we found that L is a minimum. L at 7.35 is a minimum. And we were trying to minimize the amount of paper we use. So if L is 7.35, then my outer dimension, you have to add 3 and you get 10.35. And then W is 36 over L, right, from that. So we'll do that. Okay, so 36 divided by 7.35 is like 4.89, and then you have to add 2 to it to get the outer dimension. Plus 2, and we get 6.90. So those are going to be the dimensions of the paper that minimize the area